All right, guys, welcome back. This is going to be the second part two of the 7.3 instructional videos. And what we learned in part one is we learned how to solve systems of equations by elimination. If you have not watched that yet or been for the in-person lesson, please go back and watch that. Make sure you're learning about the basics of elimination before we get into the finer points here. So what we learned in part one is we learned how to solve systems by elimination. And the whole idea being what we do to one side, we also do to the other. But that doesn't always look identical what we do to both sides because of substitution. We are doing to one side what we're doing to the other, but it won't always, it doesn't mean we're adding the exact same thing face value wise. For example, if we look at the system of equations in red, we learned in the first part of 7.3 how to solve this with elimination by eliminating the y variable by adding the bottom equation, the left side of the bottom equation to the left side of the top equation. When I would do that, I would end up with 11x. By adding the 2, the y variable is canceled, and I'm going to end up with a single variable equation. Well, what I do to one side, I must do to the other, which means theoretically I must add 2x plus 4y not only to the 9x minus 4y, but also to the 36. But we learned in the first part of 7.1 that we don't need to add the 2x plus 4y to the 36 and get a messy equation with lots of unlike terms that I can't combine, but rather I can just add 36 and 27. Why is that the same thing as adding 2x plus 4y? Is adding 27 the same thing? Because 2x plus 4y equals 27. Because 2x plus 4y equals 27, I can add 27 to 36 and still satisfy the criteria of doing the same thing to both sides of the equation. So I would do that, and I would be on my way to solving my problem. Okay, this was the introduction to elimination. If that looks unfamiliar, please go back and watch the part 1, 7.3 instructional video. You'll get more insight onto that. And what we're going to do in part 2 is we're going to continue solving systems of equations by elimination. But the problem is, and what we're going to run into, the new wrinkle kind of for 7.3 part 2 is if you're looking at the equation in black, if you're pretty good with elimination, you've recognized there's a problem. Now, maybe you haven't seen it yet, but what we know, if we want to solve a system of equations with elimination, our goal would be to add the left side of the equations together and the right sides together in order to eliminate some sort of variable. If adding doesn't work, we would maybe try and subtract. But in this case, no matter whether I add or subtract, I'll go back here, unlike the problem we saw in red, where when I added, the y variable was eliminated, if I add and subtract here, no variable will be eliminated. If I add the left sides of the equation, I'm going to end up with 12x plus 8y equals 0, if I also add the right sides. If I subtract both sides of the equation, I'm going to get negative 8x plus 2y equals negative 44. Again, both variables will not be eliminated. I have run into a problem. So what do? We don't want to solve this with substitution because there's no clear variable to get by itself. So how can I solve this with elimination? Well, I can't just immediately add and subtract. We already established that, so what can I do? Well, what we're going to do is we are going to manipulate one of the equations. What do I mean by manipulate? I mean, we're not going to, keyword being not, we're not going to fundamentally change the equation, right? These are the two lines I was given. I don't want to change one of the lines, but I am going to change how it looks. Okay? So how can we change how a line looks without fundamentally changing the line? Well, what we can do is we can multiply the entire equation by some number. And as long as we multiply the entire equation by some number and do it to the whole equation, it will not fundamentally change the line. So with that in mind, is there any sort of multiplication that could maybe help me with the elimination? Well, let's look. No form of multiplication between the 3 and the 5 will give me something nice where I can eliminate one of the y variables. Okay? Remember, our goal is to get something like negative 4y and 4y stacked on top of each other, or 4y and 4y, so that we want matching coefficients, even if they have different signs, because that's how we can eliminate. So there's nothing I can do with the y's, even with the idea of multiplication, to get rid of one of the y's. But if I multiply this 2x by 5, I will get 10x, and then I'm going to kind of be in business. The x's are going to have the same coefficient, meaning I can then subtract the x's to eliminate one of them. So I multiply both sides or all of the first equation by 5, and I get 10x plus 25y equals negative 110. Again, this does not fundamentally change the equation. When you add or subtract something, even if you would add or subtract it to every part of the equation, that will change it. It will become a different line. But if I just multiply both sides of the equation by a constant, as long as I multiply both sides by it, it's not going to fundamentally change the line. What the 10x plus 25y equals negative 110 is the exact same line as 2x plus 5y equals negative 22. Again, by doing this, I have not fundamentally changed the line, but I have changed how it appears, and now it's very clear I can get rid of the x variable by subtracting. And so now, just like we saw in part 1 of 7.3, I can eliminate one of the variables. So I subtract all the variables. I subtract the 10x plus 25y from 10x plus 3y. I subtract the left sides of the equations. And I am left with 0 when I work with the x's. 3 minus 25 is negative 22y. And 22 minus negative 110, that would be 22 plus 110. Two negatives make a positive, and I get 132. So the elimination process hasn't really changed. We just had the additional wrinkle. In order to be able to eliminate one of the variables, I had to multiply one of the equations by a number, by an integer. So I divide both sides by negative 22. Divide both sides by negative 22. And when I do that, I get y equals negative 6. Y equals negative 6. Now, I'm not done yet. That is just the y coordinate. Again, we've said it a billion times. What this is this is the y coordinate of where those two lines are going to intersect. It is the y coordinate of the xy coordinate pair that will make both of these equations true. So how am I going to find the x coordinate? Well, I'm going to plug this back into one of my originals. Plug it into an easy one as well. Don't plug it into the multiplied version of the first one if you are going to plug into the first one. I'll just go ahead and plug this into the second. 10x plus 3 times negative 6 equals 22, which means I'm going to get 10x minus 18 equals 22. Add 18 to both sides, and I get 10x equals 40. Divide by 10, and I get x equals 4. Again, we could check that by plugging the 4 and the negative 6 back into our original equations and confirming that it creates true math statements. But what we see here is that 4, negative 6 is the point of intersection. Again, we discovered that through elimination with the additional step of multiplying one of the equations by an integer so that we could eliminate one of the variables. And this is really going to be the running theme of part 2. So let's look at another example together. And if you feel like you got it, I would encourage you to pause the video and try it on your own. Even if you don't get it completely right, though, and you're not super duper confident, even if you get only part of it right and you're not super duper confident, still give it a shot. So go ahead and give this a shot on your own. Well, I'm going to talk through this in parts. So if you've gone, hopefully you've gone ahead and solved it, but maybe some of you are in the boat where you're completely honest. You're like, I don't know what to do. I can't solve this on my own. Let me give you the first couple steps. Again, I'm going to give you a chance to pause it, and then you can go ahead and try it on your own. So looking at this, we don't want to do substitution because there's no clear-cut variable that'll be nice to get by itself. And we cannot just eliminate right away like we saw in part 1 of 7.3 by adding or subtracting. Okay, I can't add the x, add or subtract the left sides of the equation and eliminate one of the variables. Negative 2 plus 7 will give me 5. Negative 2 minus 7 will give me negative 9. 5 plus negative 5 will give me 10, and 15 minus negative 5 will give me 20. Okay, so no matter what form of just straight up adding or subtracting, I can't get rid of one of the variables. So what we learned in the last example is we're going to have to multiply. We're going to have to multiply one of the equations to change how it looks, but not fundamentally change it so that we can eliminate. Well, when I look at the x variables, there's no nice multiplication by an integer that will give me something where I can get rid of my x variables kind of nice and neat. 2 and 7 don't really multiply well together. But when I look at the y variable, I notice I have 15 and negative 5. And I know that negative 5 times 3 will give me negative 15, give me that same number, same coefficient, even though they have opposite signs. And there I can be well on my way to elimination. Now, if you were struggling to figure out what to multiply by, I would encourage you to pause the video at this point, now that you know what to multiply by. See if you can't figure this out on your own. So I'm going to rewrite my equations just so they're kind of neat and orderly here. But I'm going to rewrite the second one with that 3 distributed through. And again, why I'm doing that is this is going to create the situation where I can eliminate one of my variables. Specifically, I can eliminate my y variable. Now, maybe the question you're stuck with is, do I add or subtract here? Okay, how do I get rid of it? What I would encourage you to do is the answer to that question is always going to be whatever helps you get rid of the variable. So we want to get rid of the y variable. How do we get rid of it? Well, if we do positive 15 plus negative 15 versus positive 15 minus negative 15, if you're struggling to figure out whether to add or subtract, right, the first one being adding, the second one being subtracting, I would encourage you to check both of those in your calculator. See which one will give you a coefficient of 0, so the variable is eliminated. Well, 15 plus negative 15 will give you 0, whereas 15 minus negative 15 will actually give you 30, because the two negatives become a positive. So in this case, we will want to add our equations together. And I go ahead and do this, and I'm going to get 19x. 15 plus negative 15 will just be 0. Negative 32 plus 51 is 19. Divide both sides by 19, and I get x equals 1. So by multiplying this second equation by 3, I created a situation without fundamentally changing the second equation where I could eliminate the y variables by addition. I do so, and I find that x equals 1. Now, of course, I'm not done yet. I'm not done quite yet. What I need to do is I need to figure out what my y variable will be. So I plug that back into one of my original equations. Plug that back into one of my original equations. I chose the second one, but of course not with the 3 distributed through. 7 times 1 will give me 7. I subtract 7 from both sides. I get negative 5y equals 10. divide by -5, divide by -5, and y equals -2. Y equals -2. Okay, so you again could check this solution by plugging your solution back, or by plugging your coordinate pair back into your original equations. You plug it back into the original, make sure they create two true math statements. If we did that, -2 times 1 would be -2. 15 times -2 would be -30. -2 plus -30 is -32. You check the other one as well, and we'll see that as our solution. So let's look at one more example together. Let's do a word problem, and let's really apply what we're doing. And again, I'm going to encourage you to please try this on your own. If you have not tried a problem like this on your own yet, please try it. See where you're at, okay? This will give you a really good picture of whether you're picking this concept up or not. Suppose the freshman class decides to do a fundraiser to raise money for a homecoming DJ. Since Christmas is around the corner, they decide to do wrapping paper and cards. Rolls of wrapping paper are sold for $4, and greeting cards are sold for $10 a package. All in all, the freshman class sells 205 items and makes a total of $1,084. How many rolls of wrapping paper and how many cards are sold? So we kind of got a lot going on here. Before we can ever solve this, let's identify what we're asking. They want to know how many rolls of wrapping paper and how many packages of cards are sold. So let's maybe set some variables. Maybe we'll call G the number of packages of greeting cards. And maybe we will call rolls of wrapping paper W, the number of rolls of wrapping paper. Number of rolls of wrapping paper. Okay, again, I'm going to go give those variables because that's what we're trying to find. We don't know how many rolls of wrapping paper we've sold or how many packages of greeting cards, but that's what we're looking for. And so now let's start to set up some equations. Let's look for a total in this case. Well, I actually see a couple. I see 1,084 is the total amount of money we make. And I see that we sell a total of 205 items. Now this should make sense, right? We are advanced beyond working with just single equations. We are now working with situations where we have multiple equations that we must meet both criteria, right? And my solution of the number of rolls of wrapping paper and number of packages of greeting cards must not only meet the 205 requirement, but it also must make us $180 or $1,084. Now, I think when we're setting up multiple equations, it's good to classify what the equations resemble. That way we don't confuse what we put where. So this 1,084 has to do with money, and the 205 has to do with how many physical items we're selling. So what makes up these totals? Well, we notice that rolls of wrapping paper are $4 a piece. So how am I making money? Well, I'm selling rolls. If I sell one roll, it's $4. Two, it's $8. Three, it's $12. What are we doing there? We're taking 4 and multiplying it by the number of rolls of wrapping paper. We're doing the same thing for the greeting cards. We are multiplying 10 by the number of packages of greeting cards that we sell. So 4 times W plus 10 times G will make up together that $1,084. Now we still have to work through the 205 items. So let's ask ourselves, what is making up that 205 items? Well, it's the number of packages of greeting cards and the number of rolls of wrapping paper that we sell. Okay? Notice, though, that the 4 and the 10 have no place in this equation. Why? Because the 4 and the 10 have to do with money and how much money we're making. We're not talking about money in this second equation. We're just looking at the number of items. So I now have two written equations that resemble the situation. And now what I need to do is I need to find W and G. Now in this situation, would it be appropriate to solve this system of equations, find the values for W and G that satisfy both by substitution? Yeah, W and G would be really easy to get by themselves in the bottom equation. But since we are learning about elimination here, we will practice that. And there isn't a initial addition and subtraction that'll automatically cancel a variable right away for me. Okay, well, there is no nice, neat addition and subtraction there, which means I need to do some sort of multiplication if I want to do elimination. Well, I have a couple options here. I could multiply the bottom equation by 10 to cancel out the G's, or I could multiply the bottom equation by W to cancel out the W's. Since I'm only going to have to multiply by 4 to cancel out the W's, that seems like the easiest move to me. So I'm going to rewrite my equations, not changing anything with the top one, but I'm going to multiply the entire bottom equation by 4 in order to eliminate or set up a situation where I can easily eliminate the W's. But again, what I do to one part of that equation, I must also multiply the other parts. Now I'm in a position where I can eliminate one of the variables. I'm going to eliminate the W's by subtraction, right? If I added them, I'm going to get 4 plus 4, which is 8W, and that won't eliminate it. So when I do this, 4 minus 4 is obviously 0. 10 minus 4, though, is 6G. 1,084 minus 820, that's going to be 264. Divide that by 6, and I find that G equals 44. G being the number of packages of greeting cards. So that's how many packages of greeting cards I sell to meet the requirement of both equations. But I also need to find out how many rolls of wrapping paper I sold. So I'm going to plug that 44 back into one of my originals, probably the bottom one because it's the easiest. And when I do this, I find that I need to sell 161 rolls of wrapping paper. Okay? So again, similar process. We just had the additional step of setting up the problem here to find out how many rolls of wrapping paper and how many packages of gift card or greeting cards are sold if we make $1,084 and we sell 205 items. So we multiplied the bottom equation by 4 so that we could eliminate the W variable. Once we eliminated that, we quickly found that we need to sell 44 packages of the greeting cards. And that led us to the conclusion that in turn, we need to sell 161 packages of the rolls of 161 rolls of wrapping paper as well. To make sure that our answer makes sense, let's check it. If I sell 161 rolls of wrapping paper and 44 packages of greeting cards, I will meet that total of selling 205 items. And if I make $4 off every roll of wrapping paper, and I sell 161 of them, and I make $10 off every package of greeting cards, and I sell 44 of those, I will indeed make $1,084. Guys, thanks for watching. I hope this makes sense. Again, hopefully you see it's not very different from the initial part of 7.3. We just had that added step of multiplication. Please, though, if you feel stuck or confused, email me any questions you may have.